Assalamualaikum dan salam sejahtera. Dalam video ini kami akan menerangkan bagaimana cara untuk menyelesaikan masalah linear programming menggunakan software Lindo. Seterusnya, kita akan pergi ke masalah linear programming terlebih dahulu. Okay, Delicious Bakery is a bakery that making grand wedding cakes. Every day, they produce cakes with 3 different flavors. The cakes are tiramisu cake, red velvet cake, and cheesecake. The cost for baking a tiramisu cake is Rm40 and the cost for decoration is Rm20. For red velvet cake, it costs Rm10 for baking and Rm30 for decoration. For cheesecake, it costs Rm10 for baking and Rm10 for decoration. Every day, there are only available 400 flour to use to bake all the cakes. Unit prices for tiramisu cake, red velvet cake, and cheesecake is Rm300, Rm200, and Rm100 respectively. How many each cake the bakery should produce to maximize daily profit? Okey, seterusnya kita akan membuat jadual untuk memudahkan kita membina objective function dan constraint-constraint yang wujud berdasarkan masalah tadi. Okey, berdasarkan info-info sebentar tadi, ini adalah jadual maklumat tersebut. Kita andaikan X1 sebagai tiramisu cake, X2 sebagai red velvet cake, dan X3 sebagai cheesecake. Untuk membina objective function, kita tahu bahawa objective function adalah daily profit bakery, di mana unit prices for tiramisu cake is Rm300, for red velvet cake is Rm200, and for cheesecake is Rm100. So, objective function kita adalah to maximize 300x1 plus 200x2 plus 100x3. Seterusnya adalah constraint-constraint. Constraint-constraint ini dibina berdasarkan proses-proses yang ada dalam jadual tersebut. Okey, untuk constraint pertama adalah baking process, di mana 40x1 plus 10x2 plus 10x3 less than and equal to 300. For decoration process, 20x1 plus 30x2 plus 10x3 less than and equal to 600. Dan untuk constraint terakhir, flour used, 10x1 plus 20x2 plus 30x3 less than and equal to 400. Okay, yang last sekali adalah x1, x2 and x3 is more than and equal to 0. Baiklah, seterusnya kita akan pergi kepada penyelesaian masalah linear programming menggunakan software Lindo. Perkara pertama yang kita perlu lakukan untuk menyelesaikan masalah linear programming kita adalah kita hanya perlu typekan objective function dan juga constraint-constraint yang telah kita bina sebentar tadi. Baiklah, setelah kita menaip objective function kita dan juga constraint-constraint yang terlibat, apa yang kita perlu buat adalah pergi kepada butang ini dan tekan yes kepada pop-up box ini untuk menerima sensitivity report kita. Dan ini adalah sensitivity report analysis yang telah kita dapat daripada software Lindo ini, di mana objective function adalah 4500. Seterusnya, sensitivity analysis report ini juga menunjukkan variable dan value di mana suggestion untuk daily production cake tersebut. Okay. Untuk mendapatkan maximum daily profit 4500, bakery tersebut perlu menghasilkan tiramisu cake sebanyak 3 biji untuk setiap hari, red velvet cake untuk 18 biji pada setiap hari, dan juga cheesecake 0 biji untuk setiap hari. Sensitivity analysis report ini juga akan menunjukkan objective coefficient range dan juga right hand side range.
Assalamualaikum and very good morning. So today I would like to continue the explanation about the question 3a and 3b. So for 3a, first 3A1, we need to change the right hand side but all conditions are feasible. So we create a situation which, suppose a baker in decoration cake used RM40 to decorate grand red velvet for international artist events. Will this change the optimal production quantities? What can be said about the change in total profit? So first of all is we need to find the increment. So we know that the initial decoration cake used is RM30. So D2 should be 40 minus 30 and it could be 10. So we refer to the window that we had built, that we had obtained, that we know for decoration the allowable increase for the right hand side is 14.2855714. So if we see that D2 we get 10, so 10 is within the feasibility range because the allowable increase is 14.2855714. Alright, so we also can check the feasibility condition by using manual calculation. Alright, so first we need to let D1 equal to 0, dt is equal to 10, and d3 is equal to 0. d2 is equal to 0 is equal to 10 as we obtained in the calculation before, which d2 is equal to 10. Alright, so we need to substitute the value of d1, d2 and d3 into the equation of each basic variable that we obtain for x1, x2 and x3. So x1, the equation is 3 plus 0.03 d1 minus 0.01 d2. So we just substitute the value of d1, d2 and d3 into the equation. So we obtain that the value of x1 is 2.9, which greater than 0 and it was feasible. Alright, for x2, we also substitute the value that we obtained for d1 and d2 into this equation. So we obtain the value of x2 is 18.4, which greater than 0 and it was feasible. Same goes for x3. We just substitute the value of d1, d2 and d3, which d1 is equal to 0, d2 is equal to 10 and d3 is equal to 0. So we obtain the value of x3 is 3, which greater than 0 and it also feasible. Alright, so then we need to, the current basis remains feasible with the new values for BVs, and the production quantities will change. Alright, so we know that the dual or schedule price of 5 ringgit is valid. Okay, we can check it. Okay, in this window, okay, we can see that in row 3 the dual price is 5. Okay, and we need to know what is the change of z or objective function. So we just need to substitute the value of d1, d2 and d3 into this equation, which z is equal to 4500 plus 5d1 plus 5d2 and plus 0 d3. So we obtained that the value of z is 4550 ringgit. Okay, for 3A2 it was same as 3A1, but at least we need to have the condition that are infeasible. So the situation is a consultation offers to increase the decoration of red velvet prices to 50 ringgit. Will this change the optimal production quantities? What can be said about the change in total profit? So first of all, as usual, we need to find the increment. So the new value of the decoration of red velvet price, we need to subtraction with the initial decoration of red velvet price, which 30 ringgit. So 50 minus 30, we obtain D2 is equal to 20 ringgit. Alright, so after we obtain the value of D2, we need to check either the value of D2 was in the range or not. So if we can see here, for decoration, the allowable increase for right hand side is 14.285714, but we obtain the value of D2 is 20. It means that D2 is outside the feasibility range because the allowable increase is only until 14.285714. Okay, we also can set the feasibility condition by using manual calculation. As usual, we need to let D1 is equal to 0, D2 as obtained, we obtain D2 is equal to 20, D3 is equal to 0, and we need to substitute the value of D1, D2, and D3 into the equation for all BVs, which x1, x2, and s3. So for x1, we substitute the value of D1 and D2, alright, and we obtain the value of x1 is 2.8, which greater than 0, and it was feasible. Alright, so for x2, we substitute the value of D1 and D2, and we obtain the value of x2 is 18.8, which greater than 0, and it was feasible. And s3, we obtain that s3 is negative 4. Negative 4 is less than 0, and it shows that it was infeasible. Alright, so it means that the current BV will not keep the current solution optimal. Alright, so what should we do to find the new optimal? So we need to make a dual simplex method. Alright, the value that we obtain first, D1 is equal to 0, D2 is equal to 20, and D3 is equal to 0. Also, x1 we obtain just now is 2.8, x2 is 18.4, and s3 is equal to negative 4. Alright, so we need to find the optimal tableau by using dual simplex method. Right, so to find a new optimal tableau by using dual simplex method, okay, first we had obtained the value of D1, D2, D3, x1, x2, and s3 from the calculation above, and the value of z is 4600. Alright, and we know that the BV or basic variable is z, x1, x2, and s3 here, and the value of NBV is x3, s1, and s2. Okay, so we just substitute the value of x1, x2, s3, and z as the right hand side. Okay, here 4600, 2.8, 18.4, and negative 4, and all of this is from the previous table. Okay, so step 1 is we need to check the right hand side, which one is the most negative. So we obtain here that negative 4 is the most negative right hand side, and it was s3. So we noted this as the leaving variable. So s3 is the leaving variable. Okay, next is we can see that x1, okay, in this s3 row, it was 0, 0, 24, 0.1, negative 0.7, and 1. Alright, we need to find the most negative. So if you can see here, negative 0.7 is the most negative. Alright, this is the special case, okay, because we just obtained negative 0.7, only one negative here. So next is we need to find the ratio. Okay, so to find the ratio, we need to divide, alright, the absolute of coefficient of z divide by the coefficient of s3. So absolute 5 divide with negative 0.7, and we obtain the value is 7.143. Alright, since it was only one negative at row s3, alright, negative 0.7, so as this column will be the entering variable. So s2 will enter the basic variable, and s3 will leave the basic variable. Okay, alright. To be made sure that the table has reached an optimality, alright, the condition is we need to make sure that all the value of the right hand side must be positive. Okay, after we make NERO, alright, so we obtain that the value of z is 32,000 over 7, x1 20 over 7, x2 636 over 35, and s2 is 40 over 7. Okay, as you can see here, all the value of right hand side was non-negative, so it means that the table has reached an optimality. So the new optimal value of z is 4,570 ringgit 43 cents. For x1 is 2.857, x2 18.171, and x3 is 0. Alright, for question 3b1, we need to change the objective function, but all conditions are satisfied. So this situation is, suppose the profit per red velvet cake increased by 100 ringgit. Will this change the optimal production quantities? What can be said about the change in total profit? Alright, so based on the situation, it has stated that the profit per red velvet cake increased by 100 ringgit. So it means that the increasement was 100. So we refer to the Lindo. Alright, so for the objective coefficient range for red velvet cake is the allowable increasement was 250 only. Alright, since we obtained that the value of the increasement is 100, meaning that G2 is within the optimality range up to 250 ringgit. Alright, we also can check the optimality condition by using manual calculation for all BVs which S1, S2 and X3. Alright, so we let D1 is equal to 0, D2 as we obtain is equal to 100 and D3 is equal to 0. So we just substitute the value of D1, D2 and D3 into the equation for each BV. For S1, we obtain that S1 is equal to 3 and it was greater than 0, means it was satisfied. S2, we obtain S2 is equal to 9, also greater than 0 and it was satisfied. And X3 is equal to 20, which is with greater than 0 and it also satisfied. Alright, so based on the calculation and the Lindo, we know that the current BV remains optimal because the allowable increase is 250 ringgit and it was within the range. Thus, the optimal production quantities will not change and the total profit of Z will increase by 100 per cake produced. So, X1 is equal to 3, X2 is equal to 18 and X3 is equal to 0, as we can see here. X1 is equal to 3, X2 is equal to 18 and X3 is equal to 0. Alright, we show it here. And the value of Z is 300 X1 plus 200 plus 100 X2 plus 100 X3. So we just substitute the value of X1, X2 and X3 that we obtained here, 3, 18 and 0 into the equation and we obtain the value of Z is 6,300 ringgit. Okay. For question 3b2, we need to change the objective function but at least one condition unsatisfied. Alright, the situation is if it costs 200 ringgit to produce tiramisu cake for n year promotion, will this change the optimal production quantities? What can be said about the change in the total profit? Okay, so we know that the initial cost is 300 ringgit. So we need to find the increasement or decreasement. So 200 minus 300 and we obtain the value of G1 is negative 100. So we need to check the decreasement of tiramisu that we obtain in Lindo. Alright, so if you can see here the objective coefficient range for tiramisu, the allowable decreasement is 0, meaning that it can be decreased. Since we obtain that the decreasement is 100, so D1 is outside the optimality range and not allowed to decrease because the allowable decreasement is 0. Alright, so this shows that the current BV will not keep the current solution optimal. Alright, we also can check by using manual calculation to find the optimality condition. Alright, so we obtain D1 is equal to negative 100, D2 is equal to 0 and D3 is equal to 0. We just substitute the value of D1, D2 and D3 into the equation of all BVs here, S1, S2 and X3. Alright, so we obtain the S1 is equal to 2 with greater than 0 and it was satisfied. S2 is equal to 6 which greater than 0 and it also satisfied. But x3, we obtain that x3 is equal to negative 20, which less than 0, and this is not satisfied. Alright, so we need to find a new optimal tableau. Alright, so to find the new optimal tableau, we need to make a simplex method. Alright, so first of all is substitute the value of z, x1, x2, x3, xbv, and the nbv here, the right hand side that we obtained just now. Alright, so here 4,500 for z, and the right hand side coefficient. Alright, so 3, 18 and 10 and 0, 3, 18, 18 and 10. Okay, 3, 18 and 10. Okay, so first we need to find the entering and leaving variable. Alright, so first of all, in the row 0 here, 0, 0, negative 20, 2, 6, 0 and 4,500. Okay, we need to find the most negative. So the most negative one will be the entering variable, and after that we need to find the ratio to check and to find the leaving variable. So all the right hand side here from x1, x2 and x3 must be divided by all the coefficient of this column. So 3 must divide by 0.2, 18 must divide by 0.2, and 10 also must divide by 24. And after that we obtain the value of ratio. We need to find the smallest one. So compared from 15, 19 and 0.417, the most smallest is 0.417. So S3 will leave the variable. So it was the leaving variable lah. Alright. Okay, and then we make NERO. Okay, to obtain the optimality when all of the row 0 was non-negative. Okay, and we obtain that the value of x1 is 2.197. Alright, so here is 35/12, x2 is 215/12, and x3 is 5/12. And the optimal value of z is 4,508.33. Okay, so that's all. Thank you.